Okay, we have finished the general introduction of chemical kinetics, and it might seem strange to you that all of a sudden now we're jumping into radioactivity. Well, the reason for that is that the nucleus is totally isolated from everything else. It doesn't matter a bit what's out there in the outside of an atom. The nucleus is a little tiny speck right in the middle. It would take about 100,000 of those nuclei to stretch across the atom. So the chemistry that is occurring out in the outer electrons around an atom has nothing at all to do with what's going on in the let's see, I'm going to switch cameras. It just has nothing at all to do with what's going on in the nucleus. So a completely isolated atom undergoing chemical reaction would certainly be first order decay. It doesn't depend on interacting with anything else. So you only have a concentration of A in your rate law, and the nuclear processes are all like that. So the first order decay turns out to be one of the most simple ones, and it is the one that all nuclear processes follow. So this does fit in very well with where we are in our discussion of radioactivity and chemical kinetics. Now, the process has to take place because something is happening to a particle in the nucleus that makes the nucleus become more stable. Radioactive elements have unstable nuclei, and they can be unstable because they have a wrong or bad neutron to proton ratio, or maybe they've got too much energy. If they've got too much energy, they just simply shoot out a gamma ray, and that will lower the energy state. Gamma rays carry a tremendous amount of energy with them. So if the nucleus is in one of its high energy levels, it will just shoot out gamma rays until the nucleus, every particle in that nucleus, particles in the nucleus are called nucleons. So when every particle in that nucleus is down in its lowest energy state, then it's stable from an energy standpoint. But now, let's think about a nucleus. A nucleus is made of neutrons and protons. The protons are all positively charged, and they all repel each other. So if you imagine taking two protons very far apart and you start pushing them together, they are repelling each other. But something amazing happens when you get them a certain distance apart. When you get them a certain distance apart, they all of a sudden start attracting each other much, much more than the electrostatic repulsion between the particles. So this new force, which we can't understand, we call the nuclear strong force. Nobody really knows what it is. We just know that it exists. And it is responsible for pulling the particles together into that tiny speck called the nucleus with a density that is beyond your wildest imagination. Nothing you could imagine is as dense as the nucleus in an atom. And it's held together by this unknown or unidentified force that we call the nuclear strong force. Now, but when you put that proton into the nucleus, it's still a proton. It still has positive charges. If I put two in there, they're still going to repel each other and want to get apart. They're just being held by the nuclear strong force. Now, we can minimize that repulsion by putting neutrons in between. So I got a proton here and a proton here. I put a neutron in the middle, then the neutron helps to insulate the protons from each other. So the more neutrons we have, the more protons we're going to need to make that nucleus stable. So every atom, every isotope has a best neutron to proton ratio. In some cases, the radioactivity is so slow, its half-time is so long, it still exists. For example, I think uranium-238's half-life is something like 4.5 billion years. Well, the Earth is older than that, so we still got uranium here on Earth. If the Earth were younger than 4.5 billion years, we would have no uranium here. It wouldn't be here. It would all be have disappeared a long time ago. So the neutron to proton ratio determines the stability of the nucleus. Now, generally, if you give off light or energy, gamma rays, that doesn't change the identity of the nucleus. That isotope is still the same isotope, still has the same number of protons and neutrons in it as it ever had, but it's given off excess energy. So when gamma rays are detected, the nucleus hasn't changed except changed its energy level. But any of the other particles that are emitted from the nucleus of the atom to this outside world results in a change in the nucleus to some other element. Now, one of the models that is used to describe the radioactive process is called the liquid drop model. So what we imagine is that the nucleus is like a liquid drop. If you've ever seen mercury, liquid mercury, don't do it. It's highly toxic. So, but if you ever saw liquid mercury, you can hit a little droplet of mercury and it'll vibrate and bounce around. And if you imagine hitting it enough, it bounces and then flies into pieces. Well, we imagine the nucleus in, say, uranium is like that. It undergoes some kind of violent vibrations, and then all of a sudden, it gets to the point where it breaks apart and sends a particle out, like the alpha particle. It's very small, very low molecular weight compared to the element it came from. So when that particle is ejected, the force is internal, so both pieces get the same momentum. But the alpha particle is much lighter, and it travels most of the velocity that you see from the external world is the alpha particle coming out at near the speed of light. The remaining atom, in this case thorium, that isotope would get a little bit of an impact to the left when the alpha particle is shooting off to the right. I don't show that here because it would be too small to see in this little cartoon. So the alpha particle comes off. Now, let's think about nuclide symbols that we learned about in Gen Chem 1 as well. The nuclide symbol has a superscript. It's a mass number. It's not the atomic weight, but it's a count of the number of protons and number of neutrons in that isotope. The subscript is the atomic number. That's the number of protons. So we would write uranium. This is the most stable isotope of uranium. It is radioactive. There are no totally unreactive isotopes of uranium. They're all radioactive and unstable and give off nuclear radiation. But the uranium isotope that's most stable has 92 protons. That's the atomic number we would look up on the periodic chart. And it has a total of 238 particles. And so if I subtracted the 92 from 238, that would give me the number of neutrons. Now, when you write nuclear processes, you write an equation for them. The uranium we saw became thorium. Now, how do we know that? Well, the alpha particle came off. We know what it is. It's a helium nucleus. It has 2 protons and 2 neutrons, giving 4 particles in its nucleus. These 4 particles had to come from the uranium-238. So the other isotope, to conserve the particles, would have to be the 234 isotope, because 234 plus 4 is 238. Similarly, if I know that 2 of the protons came off with the alpha particle, 2 off of 92 gives me 90. So I can look up element number 90 on the periodic chart. It's thorium. So the nuclear processes are, you balance the nuclear equation by making sure the sum of all of the superscripts is the same on each side of the arrow, and the sum of all the subscripts is the same on each side of the arrow. Now, one of the ways that a nucleus can become more stable is by emitting a beta particle. Now, a beta particle is an electron. If you remember our discussions in Gen Chem 1, a beta particle is the same thing as an electron. It's just traveling much, much faster than usual electrons are. So it's traveling at maybe the speed of light, or near the speed of light. Nothing can travel at the speed of light. But it's traveling at maybe 40 to 60% of the speed of light when it comes out. So it's really, really moving. It's a beta particle. It's a negative particle. Now, that's coming out of the nucleus. Where can it come from? Well, it can't come from the proton. It's positive. But it can come from the neutron. The neutron can give off a negative particle. That would mean what remains is a positive particle. So it's a positive particle that has still one mass unit, one particle in its nucleus. That's a proton. So whenever this happens, the beta particle comes from a neutron becomes a proton. So the neutron number is going to go down, the proton number is going to go up. So that's going to cause the neutron to proton ratio to decrease. And again, if I know I've got a -1 here, I say, well, what can I add to -1 to get 92? Well, it'd be 93. So this is element number 93. I would need to look it up on the periodic chart. Element number 93 is neptunium. Since I didn't carry off any particles with the beta particle, I didn't carry off any massive particle. It has an AMU of 0, not an atomic, not actual mass of 0. When it's moving, it has a mass. 238 plus 0 would equal 238. So it's going to be the same isotope. And the neutron to proton ratio, if I calculate it, subtract 92 from 238, and then divide that by 92, I get 1.586 for the neutron to proton ratio in uranium, and 1.559 if I take the number of neutrons here and divide by 93. Then you see it does decrease. And that may not look like much, but that's a significant amount of change. So if the uranium atom is unstable because the neutron to proton ratio is too high, one of the ways it can eliminate that is by beta emission. It can emit a helium nucleus, an alpha particle, from the nucleus of the uranium as well. And again, helium has 2 protons and 4 particles. So if I took 2 protons from 92, that would give me element number 90. I'd look it up, that's thorium, like we saw in the earlier cartoon. And 4 plus 234 would be 238. So it's the 234 isotope of thorium that would form from uranium-238. And it does cause a neutron to proton ratio. Again, we calculated it up here at 1.586 for the 238 isotope of uranium. But if you now take the number of neutrons here and divide by 90, you get 1.6. So it does cause the neutron to proton ratio to increase. You can emit a neutron, and of course, if you emit a neutron, the neutrons go down, protons stay the same, so it's going to decrease the neutron to proton ratio. The only thing that's going to happen here, though, is you change isotopes. You change from the 238 isotope to the 237 isotope. And that would cause the neutron to proton ratio to decrease as well. And if that is what needs to happen, the 237 isotope could also emit a neutron and become 236. The 236 could emit a neutron and become 235. So in any sample of uranium, these other isotopes do exist. But the 235 isotope is of special interest because if you take the 235 isotope and add a neutron to it, it becomes uranium-236. 236 decomposes the instant it's formed, and it breaks apart into two big pieces. It doesn't just emit an alpha, beta, or gamma. It breaks the nucleus right in half, or in near half pieces, lots of different fragments. And this is a process called fission, and it is the process of the first atomic bomb, was fissioning uranium-235, and it produced a whole bunch of stuff when it happened, and an awful lot of energy. The energy of the atomic bomb was generated by that. But we don't make the uranium-236. If you do, you're going to blow yourself up if you get enough of it in there. But instead, you use the 230. You can make the 235, and as long as you're careful to store it properly in small amounts, you can make it. But if you ever put, I think it's 13 pounds, but if you ever put that much, called a critical mass, of uranium-235 together, it will undergo the mushroom cloud explosion. So the secret of the atomic bomb is when you drop it, you take two subcritical masses or a subcritical mass and collapse it into one particle, one lump, and then it explodes. Okay. Now, another way is to emit a positron. A positron really is an anti-electron. Antimatter really does exist, at least at this stage. In fact, we've been able, last time I looked, we had been able to make even anti-hydrogen. Now, the process that happens when matter touches, physically touches antimatter, both pieces disappear. So if you took a positron, an anti-electron, and caused it to physically contact an electron, and since everything in every piece of matter you see has electrons in it, so if you generate a positron in this universe anywhere, it's not going to last long. It's going to bump into an electron, and the two particles disappear out of this universe completely. Now, in order to conserve energy, what has to happen then is that the energy equivalent of the positron and electron remains in this universe as energy. And in order to conserve momentum, there's a strict requirement that the gamma rays that are produced have to be produced at exactly the same instant, traveling exactly the same opposite directions. And that will conserve momentum. And this does happen. There are many elements that emit positrons, and so we observe them interacting with matter and annihilating each other. It can be easily shown in simple cloud chambers even can show the formation or the annihilation of positrons and electrons. They do give off simultaneous X-rays or gamma rays. Now, we can make use of that. It's the basis of a process called PET scans, positron emission tomography, because suppose you've got a tumor. Well, the tumor might not be visible on x-rays. Sometimes x-rays can show them, but often they're pretty big by the time they get dense enough for x-rays to show. But you could see them much better with a PET scan. And the way it works is you give the patient a low-level dose of a radioactive element that is a positron emitter. And that's incorporated into his bloodstream. It flows through every part. But in the tumor, you've got more blood supply, more capillaries, and a higher density in that volume than you have in the rest of the tissue around it. So as that tumor is forming, the positron emission from the positron annihilation is going to occur more in that region than it does in the surrounding tissue. And now, if you have two gamma ray detectors, you have to have them physically exactly the same distance from the patient, from each other, and you click them both on and off at the same time. So if they're both on and off at the same time, you're only seeing the gamma rays that originated from the very center of that point. And you can now scan that around and map out the tumor. I have 3 sons, and my middle son and his brothers were playing out in the barn lot with a great big rope. They were doing Indiana Jones from one tree to another tree in the barn lot. And I'd told them of the danger of doing that because the rope could break. And I said, be sure to take the rope down and keep it dry and out of the weather. And of course, they didn't do it. They left it up. And they just decided, after it had been hanging there maybe a year, I don't know, they decided to go back and play on it again. Well, when my middle son was going from one tree to the other, it broke. And he landed flat of his back. And I found out later that it knocked the wind completely out of him. He couldn't breathe for what seemed to him an eternity. And his brother's up there doing horse laughs at him. But anyhow, a few days after that, I noticed him coming out of the shower with his towel wrapped around him and his back exposed. And his back was just scratched all to pieces. And I said, Keith, what in the world happened to your back? And then he started to moan and groan about how he was hurting and how he had fallen. And so I took him into the hospital, and they checked him out, and they couldn't find anything on x-rays. But he was in enough pain that there was some physical damage, they thought for sure. So they did a PET scan, PET scan of that tissue. And because the crack was so tiny, it didn't show up on the x-rays, but it did show up on the positron scan, because whenever the bone cracked, it broke the capillaries and no blood flow in the crack. So the positrons that were injected into his body didn't appear in the crack, so there was no gamma rays coming from that. So when they did the PET scan, it showed a crack. If you know, there's a little pars bone. It's got the little knobbies on the top that's over the spinal column. Well, he had a crack right in the middle of one of those pars bones. And the only thing they could do really for him was just, it was small enough it would heal. So the only thing they did was just tape him up real good to immobilize the 2 pieces, 2 ends of the break, and then allow it time to heal. Well, the long story about that is that here's a kid that was 5'8", and before this happened, he could dunk a regulation basketball on a 10-foot goal with both hands. I don't know how in the world he could jump like that. None of the rest of us could. His brothers who were taller couldn't, and but he could. But after this, when he did heal up, he's no longer in pain, but he's not able to jump like that anymore. But anyhow, antimatter does exist. So sometimes science fiction becomes science fact. Antimatter does occur. So the Starship Enterprise might be able to run on antimatter. It could get potentially up to the velocity of the ejected particle, which is a gamma ray, and in theory should be able to go near to the speed of light. Now, it doesn't include warp speed. You can't go faster than the speed of light, and we've not found a way to do that. But it makes good science fiction anyhow. The other thing that's wrong with that is that the gamma rays that come out of antimatter matter annihilation have to be going in opposite direction. The net momentum is zero. So unless you figure out a way to reflect the gamma rays as they are formed so that they both came out the exhaust, this isn't going to happen. But anyhow, it's good science fiction, one of my favorites. Okay, so this is the reaction that would occur if you had positron emission. Now, positron is a positive beta particle. It's like an electron, except it carries a positive charge instead of a negative charge. So you can get positron emission, and it would occur. It would increase the neutron to proton ratio. Again, if you calculate, you get the same thing we've got all along for 238 uranium, but it would be 1.615 for the neutron to proton ratio of proactinium that would form by positron emission. Now there's another process. It's called K electron capture. And if you remember from Gen Chem 1, the K shell is the 1s orbital. It has the highest density of electrons of any of the orbitals, but all of the s orbitals have their maximum value at the center of the nucleus. Now, I know you may have forgotten that, maybe you weren't even taught that, but s orbitals can and do penetrate into the nucleus. The ones that's most likely to be there, of course, are the ones that's most dense is the K shell. And so the 1s orbital, an electron in the 1s orbital, can penetrate into the nucleus. It can strike a neutron in the nucleus and cause the neutron, it gets captured in the nucleus with the proton, and the proton becomes a neutron. And so the neutron goes up and the protons go down, and it does cause an increase. Here's the actual number calculation when this occurs. Again, the neutron to proton ratio of uranium-238 is the same number, but look here, we make the same isotope of proactinium when this occurs that we got in positron emission. So positron emission and beta electron capture are start with the same thing and produce the same thing. So chances are, if they give off a gamma ray, they both give off the same gamma ray. But then there's another distinguishing feature for K electron capture, and that is since you knock an electron disappears out of the K shell, then an electron from above falls into the K shell. That's how we generate X-rays. We can take that same element, we can bombard it with a very high energy electron beam sufficient that it knocks an electron out of the K shell, and it produces a fingerprint X-ray for that element. And so we know from X-ray tubes what that X-ray wavelength should be. And that's exactly the wavelength of the X-ray that is produced. None of the other radioactive decays produce X-rays. They can, and most all of them do, produce a gamma ray. But none of them except K electron capture produces a X-ray. And the X-ray is proof, it's physical proof that an electron that was in a K shell no longer exists in the electron structure. It's down in the nucleus, and it has fused with a proton to become a neutron. Now, all of these can be accompanied by gamma rays, and typically they are. Whenever you produce one of these isotopes from a nuclear process, the chances of it being in the ground state is pretty small. So it's going to be produced in an excited state, and it'll dump that energy in the form of a gamma ray. Gamma rays have no particles and no charge. So the neutron to proton ratio doesn't change. The only thing is you just dump, get rid of some energy. Now, we said that for any particular isotope with a certain number of protons, you're going to need more and more neutrons as the number of protons increase in order to be more stable, because the neutrons act as insulators from the repulsion of the protons with each other that would tend to tear the nucleus apart. Now, here's a graph that shows the number of neutrons in a nucleus on the left, vertical axis, against the number of protons on the horizontal axis. For example, element number 20, if you look at it on the periodic chart, element number 20 is neon. And if you look on the periodic chart also, the atomic weight is 20.18, which probably indicates that the 20 isotope of neon, I'm sorry, I looked at 20 and that would be calcium. So let's go ahead with it. I said calcium, 20 is calcium. And if you look at calcium on the periodic chart, the most stable isotope is the 40 isotope, which would have also 20 neutrons. So if you look at this, calcium is right there at the intersection of this line and this one. That's calcium. Notice that this line is the neutron to proton ratio of 1, equal numbers of protons and neutrons. And by the time you get to calcium, that is just barely at the edge of nuclear stability for those elements. But calcium, element number 20, has several different isotopes that are still are stable enough to still be here. Now, you see each isotope has a particular half-life, and that's the time it takes for half of it to disappear. So if it has a long half-life, comparable to how old the Earth is, or longer than the age of the Earth is still going to have some of it. But if its half-life is much smaller than the age of the Earth, by now that all of the isotopes, that isotope had disappeared. So that's why you see this band of stability. There is a range of isotopes that's stable, but those above the band and those below the band no longer exist on Earth. They've all, if they ever formed, they've long since disappeared. And so you can see what we said, as you increase the number of protons to neutrons, when the proton number goes up, you need more and more neutrons. So if you look, for example, at element number 70 on the periodic chart is your terbium. On the periodic chart, the 173 isotope is the most stable. And so that's what you see right here. If you go right here to about 103 neutrons with 70 protons, would be 173. So that element right in that region of the chart is probably euterbium. And there are some isotopes that can be formed that would still exist. But if you made a lower atomic mass isotope or a higher atomic mass isotope, it wouldn't work. And there's some points pointed out on the chart. At zirconium, element number 40, the neutron to proton ratio in that region is 1.25 to 1. When you get out to 10, element number 50, it's about 1.4 to 1, 40% more. And when you get way up here to mercury, it's about 1.5 to 1 to be in that band of stability. So now, typically what we observe is that elements with low atomic numbers need about the same number of neutrons to protons to be stable. So high atomic number isotopes need a neutron to proton ratio of 1.3 to about 1.5. Above the nuclear belt of stability, beta emission is probably the one that is most likely to occur or best moves the neutron to proton ratio. If you're below it, positron emission or electron capture is probably better. And nuclei above atomic number 84 tend to undergo alpha emission as well as some of those others. So uranium is at 92, and so it does alpha emission and beta emission and positron electron capture. It probably could do all of them, really. Now, remember when we talked about the arrangement of electrons around atoms, there were certain numbers of electrons. There were 2, 8, 10, 18, 32, and 50 were elements that were not very reactive chemically. They were stable chemically if they had those atomic numbers. For example, element number 2 is helium, and it never reacts with anything under any conditions. And so there is also a nucleon number that are what they call magic numbers that are unusually stable. And they are 2, that's helium, and 8 particles. If those were 8 protons, that would be oxygen. But it could be 4 protons and 4 neutrons. If it's got nucleon numbers of 2, 8, 28, 50, or 82, they tend to be very stable, or most stable. That is, they're probably stable enough to still be here. They might still be radioactive. Even numbers of both neutrons and protons are likely to be stable, but odd numbers of either protons or neutrons are sometimes unstable, but odd numbers of both are seldom stable. And so you can look at that and make predictions as well. Okay, so let's look at this. Predict the product form when radon-222 undergoes the 6 types of radioactive decay: alpha, beta, gamma, neutron, positron, or electron capture. So let's look. If you did alpha particle, here's radon-222, and alpha would take away 2 of the protons, leave 84. 84 is polonium. And it carries away 4 particles, so 4 away from 222 gives me 218. So the most polonium, for example, is in the oxygen family, and it would do everything that oxygen does, included incorporating itself into bone. Oxygen is in there in the form of calcium carbonate, and calcium phosphate, all of which have oxygen. So polonium can do that as well. Polonium is extremely dangerous, very, very dangerous if you get it inside you. Now, I want to, at this stage, take just a moment to tell you some things that we get taught. I try to burst as many of these bubbles of misinformation as I can. But it has been said all over the internet, all over the media, that radon causes more lung cancers than cigarette smoking. That's an outright lie. Radon is a gas. It breathes in and out when you breathe. So if you get radon in your body, now if it undergoes decay while it's in there, then sure enough, you're going to produce polonium in there, and that's bad. So that's not good for you. But it is a gas. It comes in and out. So we have levels set for radon in homes, and well, in public buildings anyhow, that is lower than the radiation you get from the carbon 14 and 13 that's in your body right now. We could not go into a building that had radon emissions with the same amount of radiation you already have and will have all your life. So it's just not true. They say that you should go in, and if you find radon in your home, then you need to go under the house and you need to seal it all out so that those vapors can't come into your house. Well, maybe that's true, but I would rather take my chances with the radon than to get in under the house where the radon is there. We found it, but we didn't notice the polonium that's there. Every radon atom that undergoes radioactive decay while it's under your house is dumping particles, dust particles of polonium. So if you get under there and stir all of that stuff up, putting your plastic down, I'm not doing it. I'm going to do it. I'll hire somebody. I'm sorry. I'm not going to do it myself. Let's put it that way. But the radon is not nearly the danger that people say it is. The results, the place where they got that was some person who thought they were smart looked at people who got lung cancer from working in uranium mines in England. And guess what? They did have a lot more lung cancers than the normal population. So what's in radioactive uranium mines? Oh, radon. Yes, radon is, but all the dust has not only the elements of maybe radon still in the soil, but it also has everyone that's ever decayed has probably dumped polonium in the soil as well. And when they were digging in there to get the uranium out or whatever it was, they were breathing in radioactive dust. Radioactive dust particles that are at a certain size, if they're too big, they'll stimulate a cough response and you'll cough them out. If the particle is smaller than that, real tiny, then it's going to move in and out of your alveoli just like gases do. But if it's a particle near the size of the alveoli, then those alveoli will get those particles in and they will stay until they undergo radioactive decay. It was the radioactive dust that was causing the higher incidence of lung cancer. It was not radon. But it got reported as radon. It's been debunked years and years and years and years ago, and it's still out there with people saying things like radon causes more lung cancers than smoking. Okay? All right. Let's continue. All right. So, all right. Now, suppose we had radon and it emitted a beta particle. Well, if it emits a beta particle, the result would be francium. And if it gives a gamma ray, still it's radon. If it gives off a neutron, it's a different isotope of radon. It might be more reactive, might be more radioactive, might be less. If it undergoes positron emission, it would make actinium. And if it makes electron capture, it makes actinium as well. So these are the things that you would get, and you should be able to do problems like this for any isotope that I might give you. Here's a checkpoint on this. So if you had americium and you did the same thing with it, you should be able to figure this out. Work them out and get help with your SI leader if you're having problems, or contact me, or of course the library tutors are really good this semester. What else is formed when you radon-222 absorbs a neutron and fissions to form xenon-135 and 2 neutrons? Well, okay, let's see. We're going to get xenon-135, we're going to get 2 neutrons. So I've used 54, 2 times 0 is still 0. I've used 54 of the protons here. So if I subtract 54 from 86, that would give us the 32. So it's going to be element number 32. So we would go onto the periodic table and look at 32, and that would be germanium. Okay, now what isotope would you form? Well, we got 222, we added 1, 135, and 2 times 1. What else would go here? So again, we do the math, and what it would be is 86. So fission of radon to xenon 54-135 and 2 neutrons would produce this. Now I did it like this to show the potential for a self-sustaining reaction, because you see, if I put in a neutron and get 2 back, there's a net of 1 extra one. So the next generation could take a neutron from here and keep this process going. That's the nuclear chain reaction that is responsible for the power generation in nuclear power plants or in atomic weapons. Now, we don't use radon, it's a gas. In fact, if we made nuclear power plants gas phase nuclear power plants, it would be very unlikely they could ever undergo runaway heating. Okay, here's some the reaction for uranium-235 was in the first atomic bomb. When it absorbs a neutron, it instantly fissions to produce 3 new neutrons. So that's a gain of 2. So 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, and so forth. So now, here are some, let's back up here. Now, so what other isotope is formed? So you can work that one just like we did the other one. Predict the type of decay for boron 8, copper 68, and chlorine 39. In this way of doing nuclide notation or isotope notation, this is the mass number. And we don't show the proton number because we don't need it. We've got a symbol. Copper tells us if it's copper, it's element number 29, and so forth. So if we look at these, what would we get? For boron 8 has 5 protons and 3 neutrons. Both are odd, so we expect that to be unstable. It's below the belt of stability, so we expect positron emission for these low atomic weight elements. Electron capture if it had been a high atomic weight element. Copper 68, again, it's 29 protons and 39 neutrons. Both are odd, so we expect that one to be an unstable isotope. Again, it's below the belt of stability, and emission. If you wanted to check this out, you could go onto the periodic table, and this would be an element with 29 protons and 10 neutrons. And that clearly would be below the belt of stability. So if you couldn't look at this and tell where it is, you could actually go back to that figure that had the belt of stability on it. Chlorine 39 17 and 22. One's odd, so it's probably unstable, but it might not be. It's at the top edge of the belt of stability, and so we expect beta emission there. So that's what we would guess. Iron 56 is the most stable isotope known, but cobalt 56 is unstable. Why is that? So you should use the arguments that we just discussed to answer that question. Since iron 56 is very stable, the neutron to proton ratio must be good for that region of the periodic chart. List one type of radioactivity for cobalt 56 that would lead to improving the neutron to proton ratio. Actually, see if you can find a radioactive process that would take cobalt 56 to iron 56. That's probably the best one to happen. You can figure it out. What other isotope would be formed by your answer to number 2? Okay. Which one of each pair is more stable? Fluorine 18 or fluorine 19? 10, 118 or antimony 118? Fluorine 18 or 19, okay? Well, it's both odds. It's going to be unstable. Fluorine 19 is 9 and 10. One's odd. It may be unstable, except for fluorine. It turns out to be the actual most stable isotope of fluorine is this one, and it is not very radioactive. Well, not radioactive at all. Fluorine 19 is. Just because we make a prediction doesn't make it actually obey what we see in nature. And by the way, I very often use things that if you Google it, it will give you the correct answer that fluorine 19 is stable, but our theory predicted it might be stable and might not be stable. Okay? So I'm just saying, don't Google. All right, so here's 118 and 50. Both are even. We expect 10, 50, 118 to be very stable. And that is one of the more stable isotopes, in fact, of 10. Antimony 118 and 51, well, they're both odd. We expect that to be totally unstable. Okay, so this completes this lesson on nuclear radiation. We'll pick up with some more, and then we'll get back into kinetics as well. All right, I will post this on YouTube and give you the link. Have a great day.